And so using techniques from quantum mechanics, we were able to derive the total system partition function in 3 dimensions for an ideal gas. And so it has this sort of function. What's interesting and what's very useful about this partition function is that by performing calculations directly on the partition function, we'll be able to estimate thermodynamic properties about our system. For example, as we showed previously, we showed that the internal energy of a system can be related to the total system partition function through this relationship. And so what we could do is we could plug in the Q for an ideal gas into this relationship. And so we'll factor out the kT squared. And so what we'll be taking a derivative of, since we're taking the natural log of Q, we'll take advantage of our log rules. And we'll be taking the derivative of the following. So n, the number of molecules. And so in here, we're going to have 3/2 times the natural log of t, right? Because we'll be taking the natural log of this thing. And then everything else in the equation, since we're playing around with logarithms, we could just move it to the side. And so I'll just say that everything else in the equation is here. And so within these brackets, what we're doing is we're taking the derivative with respect to time. And so this term, or not time, with temperature. And so this term is the only term with temperature. Everything else is not a function of temperature. So when we take its derivative, it's just going to become 0. And so as a result, for our internal energy for the ideal gas, we'll get the following. N kBT squared times 3/2 times 1 over t, because that's the derivative of the natural log of t. The t's will cancel, and what we get is that for the monatomic ideal gas, the internal energy can be described by this very simple sort of relationship here. I'll talk more about this relationship and internal energy in a bit. But along with internal energy, we could also calculate the entropy of our system using our total system partition function based on this relationship. And so if we plug in, we get that we could replace the total system partition function with this expression. We have the internal energy here. Okay? And then what we could do is we could then rearrange our equation like this. And so what I'm going to take advantage of is here we're taking the natural log of a factorial. Right? And so what I'm going to employ is Stirling's approximation at this point. Okay? And so with Stirling's approximation, it's already here, within our natural log, so I'll write the natural log of our Q partition function. Okay? And by employing Stirling's approximation, the natural log, since this is on the bottom, will have a negative sign here. The natural log of n factorial we could write as n ln of n minus n. Right? So we just employed Stirling's approximation there. We have kb out here, right? And for u over t, since we previously figured out what u is, when we divide it by t, we're just going to get 3/2 n kb. Okay? Oh, and then here, I'll make it more apparent. Since we have an exponent there, we could bring that down in front of the ln here. And so within the brackets, each of these terms has an n. So our entropy, we could then write like this: nkb, open brackets, natural log of q 3d minus ln of n minus 1, or I guess now it's plus 1. And then here's plus 3/2 nkb. Right? I could write this equation in a more compact form, right? Here, since we have, we could also factor out nkb here. And so essentially, what I'll be doing is I'll be adding the 3/2 to this term here. So we now have S is equal to nkb ln of our three-dimensional partition function ln of n plus 5/2. Okay? Alright, and so at this point, what I'm now going to do, well, just to avoid confusion, what I'm going to do here, this 5/2, it's the same thing as saying you have the natural log of the exponential of 5/2. Right? It's kind of a weird way to state that. But if I state it like this, I could then combine terms in the natural log. The other thing I'm going to do now is I'm going to plug in for a three-dimensional partition function. So I'll plug in everything except the n power there. And so when I do that, I get that S is equal to nkb ln of 2 pi m kbt divided by h squared to 3/2, and then here we'll have the exponential of 5/2 divided by n, and then that's multiplied by v. Okay. And so by combining quantum mechanics and thermodynamics, we now have a way to directly count the entropy of a system based on things like the mass of the particles and the number of particles and temperature, and also the volume of the system. Alright, this is a very powerful equation, and it actually has a specific name. It's known as the Sackur-Tetrode equation for entropy of an ideal gas. Okay? Alright, we could also rewrite the Sackur-Tetrode equation in terms of internal energy. So our entropy could take on the form like this. S is equal to kb n, and then we're going to have ln. And what we'll do is we'll substitute some terms in there. Anytime we end up with a 3/2 nkbt, we'll plug in u. And when we do that, we end up with the following: u divided by n raised to 3/2 v over n close plus 3/2 kbn and 5/3 plus ln 4 pi m 3/2 there. Okay? Alright, so this is just a sort of alternative form of the Sackur-Tetrode equation. Alright? And both of these forms are going to be useful for performing thermodynamic transformations.